The recent confirmation of flight testing for a second J-36 prototype, equipped with a newly observed engine variant incorporating two-dimensional thrust vector control nozzles, signifies a pivotal transition within the program's development timeline. This evolution from a first prototype, which likely focused on validating the fundamental flight characteristics and structural integrity of the novel airframe design, to a second prototype dedicated to integrating and testing a specific, high-performance propulsion system, indicates a deliberate and accelerated testing methodology. The program's progression into this phase demonstrates a systematic approach to de-risking the most complex technological elements of the aircraft in parallel, rather than in sequence, which is a strategy employed to compress the overall development schedule and advance more rapidly toward initial operational capability. The specific technological feature under examination, the two-dimensional thrust vector control system, represents a significant advancement over previous propulsion configurations. Unlike simpler, single-axis vectoring systems that primarily influence an aircraft's pitch, a two-dimensional system provides control authority in multiple planes, typically pitch and yaw. This capability allows the aircraft's flight control computers to use the engine's thrust as a primary control effector, directly manipulating the direction of the exhaust plume to induce rotational forces on the airframe. The practical implication of this technology is a profound expansion of the aircraft's controllable flight envelope, particularly in post-stall regimes and at very high angles of attack where traditional aerodynamic control surfaces, such as rudders and elevators, experience a dramatic loss of effectiveness due to disrupted airflow. In these conditions, thrust vectoring becomes the dominant method for maintaining stability and executing maneuvers. This grants the aircraft a capability known as supermaneuverability, enabling it to perform rapid, off-boresight pointing maneuvers that can provide a decisive tactical advantage in close-range aerial engagements by allowing the pilot to achieve a weapons lock solution on a target more quickly than an opponent relying solely on conventional aerodynamics. The deployment of a second flying prototype is a critical enabler for this complex phase of testing. It facilitates a division of labor within the overall flight test campaign. One airframe can continue to explore the outer boundaries of the flight envelope, testing limits of speed, altitude, load factors, and flutter, while the second airframe concentrates exclusively on the integration of the thrust vectoring system with the Digital Flight Control System (FCS). This integration is a monumental software and hardware challenge. The FCS must act as a unified controller, seamlessly blending inputs from the pilot's stick and pedals, data from the inertial reference system and air data probes, commands to the mechanical control surfaces, and now, directives to the thrust vectoring nozzles. All of this must be processed in real time to produce stable, predictable, and safe aircraft behavior across all flight conditions. Testing this intricate system on a dedicated platform isolates variables and allows engineers to gather clean data on the performance and reliability of the thrust vectoring system itself, without the confounding factors of simultaneous envelope expansion tests on the same airframe. Furthermore, the successful operation of this specific engine variant in flight points to substantial maturation in several ancillary technological domains. The mechanical actuators responsible for moving the two-dimensional nozzles must be exceptionally powerful and responsive to handle the extreme forces and temperatures of the exhaust stream while maintaining precise control. The engine core itself must be robust enough to tolerate the asymmetric and dynamic back pressures induced by vectoring the thrust, without suffering compressor stalls or flameouts. The development of such an engine indicates significant progress in metallurgy, turbine design, and full-authority digital engine control. The fact that this system is now being evaluated in flight suggests a high degree of confidence in its ground testing results and represents a major milestone in the propulsion system's development cycle. The current state of the J-36 program, as evidenced by this second prototype, is characterized by a deep and focused effort to validate one of its core performance-enhancing technologies. The program is no longer merely demonstrating that the aircraft can fly, it is now systematically proving that the aircraft can perform at the extreme edges of aerodynamic capability. The dedicated testing of two-dimensional thrust vector control underscores a design philosophy that prioritizes superior low speed and high angle of attack controllability as a fundamental tenet of the aircraft's combat effectiveness. This structured, multifaceted test campaign, leveraging multiple specialized prototypes, reflects a sophisticated and well-resourced development model aimed at delivering a next-generation air combat platform with a clearly defined and technologically advanced performance attribute.